Hi, everyone. Thank you very much for joining this talk. I'm very excited about the subject today. I think we have a lot to talk about. So I'm going to be introducing this notion of verification theater as it applies to cryptographic libraries, especially cryptographic libraries that advertise some degree of what's called high assurance cryptography or formally verified cryptography. And so in this talk, we're going to discuss this promise of formally verified cryptography. We're going to go through the verification boundary that typically envelops these cryptographic primitives and implementations. We're going to disclose a lot of vulnerabilities that were found around that boundary and then within the boundary. And we're going to discuss also what happened when we tried to disclose the vulnerabilities to the vendors, and more so discuss in a general fashion the notion of verification theater and provide some recommendations for industry best practices. So this paper, this talk is based on, or is for a paper that's currently on ePrint and is currently under peer review for publication in a journal called Verification Theater, False Assurance and Formally Verified Cryptographic Libraries. But you can basically access the full paper today at this URL. So please feel free to do so if you want a more thorough and precise accounting of all the work that's been done here. So just to be clear, all of these slides and the paper were sent to Cryspen 10 days in advance of this presentation, and Cryspen was given the opportunity to review every claim and to point out any statement they believe to be false or misleading so that corrections could be made before the talk. Cryspen was also invited to join this talk and to give their perspective during the Q&A session. So this is the target of this was the target of this research. So Cryspen is one of the small handful of vendors that are working on what's called a formally verified cryptographic library. So what's a formally verified cryptographic library? It's basically a library that uses some sort of mathematically well-specified methodology in order to give you high assurance guarantees on the correctness and the security of cryptographic implementations against certain classes of bugs. And I'll talk more about these bugs in a moment and define them. Their library is called libcrux, and they have other libraries like hpke-rs. And these are libraries that are deployed in a lot of places. Google's the cryptography team wrote a blog post about how they're collaborating with Cryspen in order to deploy libcrux for their post-quantum cryptography internally. And some of their other libraries that were targeted in this research are also used today in Signal, the Signal Messenger, and also OpenMLS, which is a group secure messaging library that's used by a lot of applications. It's a core library for the message layer security protocol. So the thing with formally verified is that the entire sort of appeal is based on the notion that when you say formally verified, people hear that it's proven correct. It's intrinsically resistant to certain types of bugs. You know, you can't have side channel attacks, or maybe you can't have incorrect implementations that violate the spec. And so this interpretation is heavily encouraged in the industry, but as we will see, it is also often wrong. So what formal verification claims to do, or actually does in some cases, is that you can prove that your primitive is functionally correct. So the primitive adheres to a specification. If I implement MLChem, it's MLChem 100%. There's also, I can prove that I've eliminated issues regarding memory safety. So there's no panics or buffer overflows, stuff like that. I can also prove mathematically that I have constant time behavior, which eliminates side channel attacks and timing attacks. However, it's important to note that in the vast majority of cases, what is not proven includes things like the fact that the compiler will behave as you expect it to behave, that platform intrinsics, so basically the way how you expect certain operations to be handled at the CPU level, will occur correctly, that the protocol logic itself is correct outside of the primitive, that the specification is complete, that your proven specification actually covers all the use cases that you have in mind, and also that the wrapper for the specification, of course, that almost always lies outside the verification boundary. So the verification boundary is the interface between code with machine check proofs, so the code that's actually supposed to be verified, and the code that's trusted without them. So there's always a verification boundary, and one of the more important questions that we're going to be covering today is whether this verification boundary is honestly communicated. So basically the way that Cryspen code works, or libcrux code works, is that you have the specification in the language like F* or lean, and this basically mathematically specifies how a primitive is supposed to exist, like the mathematical specification of MLChem or curve 25519 or stuff like that. And then from that, you extract the Rust implementation, or you model a Rust implementation in tandem with it, depending on your approach. And you also have an F-star model that's automatically extracted from that. And the F-star model type checks its type checks using the ZUG3 solver. So in F-star, types are proofs. But if you'll notice, at every step of the way here, we have an open question. Like when we're talking about the specification, is the specification complete? When we're talking about the extraction of the F-star model from the implementation, is the extraction faithful? And then when we're translating to the deployed binary, will the compiler preserve the semantics and preserve generally what behave as we expect? And the F-star team has been busy for decades, at this point, making sure that every single one of these things is addressed as much as can be. And so, for example, you have the low star language, you have the caramel compiler, and you have all of these peer-reviewed publications that target and try to whittle away at all of these questions in order to make sure that they're addressed as comprehensively as possible. Okay. However, when you actually are executing the code, the thing is that when you're talking about libcrux, as it turns out that the verified core actually only covers MLChem, MLDSA. So this is the post-quantum key encapsulation mechanism, and MLDSA is the post-quantum signature scheme that was standardized recently. Cha-Cha-20, which is a stream cipher, and Poly 1305, which is a authentication code. Primitives, API wrappers, and other important primitives, right? Like ED25519, I think at this point sees maybe a lot more use than MLDSA. Certain protocols like the PSQ post-quantum protocol layer, MLDSA signing, verification, and signature encoding, the entire ARM64 backend, and so all of this stuff actually turns out to be not verified, even though it's within a library that's marketed as having every component that's formally verified, right? And so if you actually look at the code more closely, you'll see that only a fraction of it is, well, a majority of it is formally verified, but a substantive portion of it lies outside of the verification boundary. Okay? So the vulnerabilities that we're going to be discussing today actually are so diverse that they help us develop and introduce a new taxonomy for how to think and how to reason and how to classify formal verification sort of audit findings when it comes to high assurance cryptography projects or libraries. And so we'll be talking about bugs that are at the protocol or application logic or at the unverified implementation layer or at the platform abstractions layer. And so all of these lie outside of the verification boundary, but we'll also be talking about bugs that are at the verification boundary or even within the verification boundary. And I won't really go into detail explaining all of these different categories now, because we're going to be covering them with examples as I talk about the bugs. So let's start with 9 vulnerabilities that were found, and none of them were caught with formal verification in this case study, which is libcrux and some other libraries that are being marketed by Cryspen today. So the first, by the way, 2 of these were actually not found by me. So we're only including them here because they motivated this audit and because they help inform the taxonomy. So I'm going to start with the 2 bugs that were not discovered by me, but actually discovered by other researchers last year. This first one was discovered by a security researcher named Filippo Valsorda, who is known for working on the Go cryptography libraries. So this first bug, which sort of piqued my interest and motivated a lot of this audit, was concerning the fact that the MLDSA implementation, so that's the post-quantum signature scheme, was actually producing different outputs on different platforms given identical inputs. So if you run it on x64, which is what's used by most laptops today, you will actually get a certain output, the correct output. But if you run it on another CPU, namely an ARM64 platform, you will get an incorrect signature. And so for me, that was weird because I thought, that's odd. I'm actually quite familiar with Cryspen's work. And I was surprised to see that this bug, which appears to have been found by accident, was able to go through their formal verification pipeline. And it turns out that if you look closely enough, just assume to be true, and there's no formal verification that's happening here. And so this is a type 1 boundary failure. The platform abstraction itself was not verified. So if you look at the thing here, this goes at the bottom with unverified platform abstractions. That's what introduced this vulnerability. It's still outside the verification boundary, but we'll get to that in a moment. Okay. This bug was fixed, and we'll talk more about the way that the disclosure of fixes was handled later in the presentation. So in a proof system, an axiom is a statement that's accepted without a proof. And this is what's happened here in this bug. If an axiom is false, you can basically derive anything. And so here we had a bunch of ARM64 intrinsics that were all labeled as admitted as true immediately as axioms. And so the formal verification here was basically skipped entirely and was totally meaningless. Hence the existence of this bug, and which is, what's really interesting about this bug, I should note, is that this is a bug that would have been caught by unit tests, right? So the most basic unit test would have caught this bug, but the over-reliance on formal verification here, to the point of ignoring standard engineering practices, led to this bug actually escaping these more advanced, I guess, methodologies. And this would have been caught if they just had relied on, or even had, in addition to their methodology, more basic things, like just having unit tests or integration tests or stuff like that. The other bug is kind of similar. This is by an anonymous GitHub user named, I hope I'm pronouncing this correctly, Gu Jiang, also in December 2025. The first one was in November. So the portable MLChem implementations, byte serialization and deserialization functions used the different endianness than the SIMD backends. So SIMD is an optimization technique, a low-level optimization technique. And so basically what this meant is that depending on how you serialize and deserialize, you can actually end up with decryption failures. And this was actually a bug in Signal. So Signal used this library. They used this implementation of MLChem. And Signal was experiencing silent decryption failures as a result. And this was filed in Signal. And they had to fix it. Signal fixed it. And Cryspen fixed it as well, although no advisory has ever been issued for this bug, including up to this day, as I give this talk. And so again, the API for this code existed in over 3,000 lines of code that was never extracted to F star. So it was never part of the verification pipeline, right? And this is, again, an unverified platform abstraction vulnerability. So those two bugs, again, first bug is Go researcher Filippo Valsorda, Go cryptography engineer, rather, Filippo Valsorda. And this second bug is by Gu Jiang, an anonymous GitHub user. From now on, it's bugs that I actually found as part of this work. So the first bug is interesting because it's actually a complete violation of the specification. So they were implementing a IETF RFC for a primitive called hpke, and this is a hybrid public key agreement primitive that's specified in an RFC. And the way that it's specified means that you have to validate X25519 public keys. And so some people think this is necessary, some people don't, but that's not important right now. What's important is that this is how the specification defined it. And even though it was defined that way in the specification, that definition never reached the implementation. And so we had an implementation that was not adhering to the specification, not validating these points, could in certain protocols introduce the risk of a small subgroup attack. And so this risk was potentially present here. And all of it completely sidelined the formal verification pipeline. And so this is a good example of a type 2 boundary failure, where the protocol logic itself doesn't actually benefit from the formal verification, despite it being part of a stack that has formally verified components. And so for that reason, this bug was never caught, even though like you're implementing the spec, but you're just not implementing it correctly, and you're implementing that, you're not implementing it completely, rather, and that incomplete implementation lies outside of the verification boundary. The fourth bug, and this is a really, really big one. So again, in hpke, they had a nonce reuse vulnerability. So this is a catastrophic vulnerability, because what happened was that they had basically some code that would check whether the counter was incremented enough in order to reach a certain limit. And if it reaches that limit, an error is supposed to be thrown. But the counter itself checks for a value that the sequence number will never reach, because the sequence number is defined as a U32. And so the maximum value of a U32 is 2 to the 32 minus 1. but the check is actually looking for a value that's closer to, I think, 2 to the 128. And so it simply will never reach. Actually, 2 to the 96, yes. So 2 to the 96 is what the spec asks for. And so that's never going to be reached. And so actually, if you just send more than 2 to the 32 messages, you will trigger a nonce reuse vulnerability. And that means that you can retroactively decrypt all previously sent messages, as well as forged messages. It is a catastrophic, critical vulnerability. And again, this was not caught. The impact here, I can't overstate the impact of this vulnerability. So this was also fixed eventually. Vulnerability number 5, we had a ECDSA signature malleability issue. So this is, I have to admit, it's contended whether this is a vulnerability or not, because this is a question of norms. So the way that ECDSA exists, according to the specification, is that it's basically malleable, which means like I can have 2 signatures for the same payload, and that's supposed to be sort of acknowledged as part of how ECDSA is defined. However, the way that ECDSA actually ends up being used in the real world means that for a majority of cases, you actually have to account for this. There are reasons to account for this in cryptocurrency, because with, if you remember the Mt. Gox hack, it was actually possible because of this bug. And many cryptocurrency exchanges, especially in the case of Bitcoin, were actually taken advantage of and exploited because of the fact that ECDSA is malleable. And so it became a norm in the industry to watch out for malleable signatures in ECDSA, not just in the context of cryptocurrency, but also in the context of software updates or CT logs, and there's a whole bunch of examples, bank transactions that one can give relating to how this can be important. But strictly speaking, you're actually, here's what's interesting about this. Strictly speaking, you actually are adhering to the spec, right? And so Cryspen decided that they won't fix this, and to be honest, like I won't complain about that. Like that's reasonable, because here we have something that's provably correct with regard to the specification, and the specification is actually fully correctly implemented, but you still have real-world bugs. Because the intuitive understanding of how a signature is supposed to work is that I have a signature for a thing, and there's only one signature for one thing, right? But that's not the case here. You can actually have 2 signatures for one thing. And so there are checks that prevent this from being possible, but they weren't implemented in this case. And so even though you actually did everything correctly, you can still have a primitive that, because it sidesteps what have become norms in the industry, can still create risk if deployed in certain, well, many different use cases. It's not, these are not edge cases like cryptocurrency and banking and CT logs. It's not like there's one specific use case in which this becomes a vulnerability. Even more examples of ways that we can flout the verification boundary. So ED25519 has a step in its specification where you're supposed to do something called clamping. And so this clears a bunch of bits and sets a bunch of other bits. And so they basically did that twice. And so why did they do that twice? I have no idea. But it did result in a slight reduction of entropy in the seed, so the secret value, from 256 bits to 251 bits, and for no benefit. I don't know why this was done. So clamping is usually done on the hash output when you're doing ED25519, not on the seed. But they did it on both. And so this is an example of an unverified wrapper logic. So the verified function, secret to public, actually correctly implemented the hash then clamp, so they actually clamped at the right time. But the wrapper itself pre-clamped things for some reason, right? Even though the clamping on the seed level would actually never translate into anything useful. So you're not actually, it's not a defense in depth measure. It doesn't really do anything, right? Okay. So here's another more serious one. You'll note that just to prevent any sort of drama, I didn't even bother to assign any severity to these vulnerabilities, but the nonce reuse one is pretty critical, and this one is pretty severe as well. I would argue critical as well. So it turns out that in libcrux's post-quantum protocol, you can actually cause a denial of service just by sending a AES GCM ciphertext that had an invalid tag. Because if you do that, the Rust code will call unwrap and the entire thing will crash. So one sort of result from this is that the entire implementation becomes not even NCCA secure, because you obtain a distinguisher, and you can, aside from, of course, causing the entire thing to crash, which is an obvious denial of service and a really bad deal, just by sending an invalid ciphertext, which is something that any attacker, any active attacker can do, you can also obtain a distinguisher. And so this affected half of all PSQ cipher suites, because half of them depended on ASGCM. And what's really interesting about this vulnerability is that the correct code was right there, visible here in yellow. But for some reason, it was commented out, and you had this incorrect code, maybe something carried over from debugging, I'm not sure. But it reminded me of the go-to-fail vulnerability from Apple, which also similarly, like, it was more of like a copy-paste issue that caused a catastrophic bug. So this was also eventually fixed. Finally, well, no, we actually have way more. We have MLDSA verification. So in MLDSA, you're supposed to have norm checks. And if you don't have a norm check, you're actually able to create signatures that will be accepted by this implementation of MLDSA, despite being rejected by other ones. And so let me give you a real-world use case where this can be a severe vulnerability. So if anyone here is familiar with the way that cryptocurrency validators are implemented, sometimes, for example, for Zcash, you'll have, or for Ethereum, you'll have a validator that is implemented in Go, and another one that's implemented in Rust, and maybe a third one that's also implemented in Rust, or maybe a fourth one that's implemented in C or some other language. And so you'll have different validator implementations. And so there was a really interesting blog post by Henry de Valence a couple of years ago that showed that the Zcash ecosystem, I believe, was fragmented based on which implementations of validators would accept which signatures. They all implemented the same signature scheme. I think it was either ECDSA or ED, I'm sorry, I don't remember, or ED25519, but some of them would accept certain signatures and some of them would reject them, and there was, this was because the spec wasn't particularly precise about what constituted a valid signature. In this case, the spec was completely precise. So what happened was that there was dead code that wasn't called, and so what this meant was that you essentially obtained a split on what was considered a valid signature and what wasn't. And so if you had certain validators or certain nodes in any cryptographic system that had implementations that depended on this implementation of MLDSA, libcrux's implementation of MLDSA, and others that used correct implementations, the correct implementations would reject these signatures, but these signatures would be accepted by the MLDSA, by the libcrux MLDSA implementation, which would result in inconsistency. And so again, this is supposed to be in a formally verified library, but it's right at the verification boundary. And so you still end up with a really serious vulnerability that creates a cryptographic inconsistency with the rest of the ecosystem. And this is still has not been fixed today, even though I think it's been more than 2 weeks, if I'm not mistaken, since it has been reported. Here's another one. So this is the final one, I think, regarding the bugs that lie at the verification boundary or right outside the verification boundary. So this one is relating to the fact that the deserialization of hints in MLDSA was missing a bound check. And so again, this actually targets, this makes MLDSA signatures somewhat more malleable. And so you can actually obtain 2 valid signature records for the same artifact. And this is similar to what I discussed earlier. And again, this is not yet fixed, and it's right at the verification boundary of what was supposed to be a formally verified library, right? And so the reason why discussing these bugs is important is because it's important to see, it's important to really understand the limits of formally verified implementations. One really pervasive symptom in the domain right now is that you have cryptographic libraries that advertise themselves as high assurance, and you have the rhetoric that like every component is formally verified, and then like in a footnote within a footnote within a footnote, you see that actually that's not as general of a statement as one might expect it to be, right? And so here in this case, like just looking at MLDSA, we have certain components that are verified, like the SIMD arithmetic, the number theoretic transforms, the encoding primitives, and the type definitions. But those are actually just, the leaves, so to speak. The roots, which are the signing algorithm, the verification algorithm, the signature encoding, the key generation, like these are some pretty big, pretty central components, are actually not verified, right? And so basically, as noted here in the slides, it's basically saying when you say no bugs are present in the verified code, you're basically saying no bugs are in the parts that we checked. But the parts that are actually checked and the parts that are implicitly advertised to be checked turn out to be two very different things, right? And so let's look at the summary of these bugs. So these are all bugs that were found within a library that's advertised as formally verified. And again, I want to be clear here. So we have more bugs that we're going to talk about in a moment. But these bugs were not inside the verification boundary. These were bugs that were outside the verification or right at the verification boundary. But they're still really important because they illustrate the limits of formal verification today or of formally verified cryptographic libraries today. And they furthermore illustrate the importance of clear and honest communication about that. And so because if you don't communicate very honestly, you might end up in a situation where you have nonce reuse in a library that's being used by Signal or OpenMLS or Google, or you have an NCCA violating implementation of a library, or you have a deviating, incorrect, malleable MLDSA implementation. And so people are going to trust you to implement what have been standard best practices in cryptography for over a decade, like unit tests, when you're providing a cryptographic provider that gives you all of these primitives, and especially when you say that you're formally verified. And in these cases we didn't even have that. And I don't know, maybe in some cases they did, but in that case I wouldn't even understand how a unit test wouldn't catch a lot of these bugs, especially the bug that was initially reported by Filippo in November 2025 regarding the incorrect MLDSA output on certain platforms, right? And so the most dangerous bugs here, of course, remain the nonce reuse, which leads to full plaintext recovery and universal forgery with just 2 to the 32 messages, and the full crash and distinguisher just by sending a malformed ASGCM ciphertext. And so again, I just want to stress these bugs were in production code. Cryspen has said like, oh, we version our libraries as being like version 0.1 or whatever, and that means you shouldn't take them seriously. But then they also lobby for the libraries to be used by Signal and Google. And so, yeah, I don't know which I should take more seriously here. So let's talk about the disclosure. What happened when I reported these bugs? So in November 2025, and again, this is what motivated this research, when Filippo Valsorda reported his initial bug, Cryspen didn't issue a security advisory. The only security advisory that's in existence even today, almost a half a year later, was actually published by a third party. Security engineer Joe Burr-Pixton, who is known for the Rust TLS library, TLS library for Rust, published a third-party advisory in the RustSec security database. And I'm still trying to get them to publish a advisory for some of these vulnerabilities today. And so contrast this with some of Cryspen's own research. So Cryspen was actually part of the hpke-rs research alongside other researchers, including, I think, Daniel Bernstein and some other researchers. And in hpke-rs, they found some timing attacks in MLChem implementations and Kyber implementations. And so at that point, the Cryspen researchers, alongside their collaborators, made an entire tracking website, contacted everyone, encouraged everyone to publish security advisories and announcements. And so here in this case, they didn't do any of that. But when it comes to research that they do, they expect their peers to do the same, right? To actually do all of these things. Let's look at, so this is the most damning slide, I think, in the entire presentation. So when Gu Jiang, apologies if I'm mispronouncing that, filed his endianness bug, the cross-backend endianness bug, which was linked to Signal decryption failures in production. So the moment that the bug was filed in libsignal, Cryspen's CEO changed the title of the bug filing to remove the words critical bug, and otherwise kept the title the same. So, and that was all the acknowledgement that the bug got from Cryspen. To this day, there is no advisory for this bug, or even any formal or informal acknowledgement that this bug ever existed, even though it led to decryption failures in Signal in production. The only reaction was to remove the description of it as a bug when this libsignal library was tagged. And Gujiang, I want to be clear, presented this bug as a pull request. Filippo also presented his bug as a GitHub issue. And so these were like good faith presentations, and no security advisory was ever issued for any of these bugs by Cryspen. The first one only by a third party, and this one by literally no one ever. So this is, I mean, I really don't like this. I really don't like this sort of behavior, honestly. Now getting to my bugs. So these were the first two bugs which I did not discover, and now we're talking about the bugs that I actually found. So in February 2026, I submitted in the same day an initial set of pull requests, 4 pull requests for 4 bugs. The first one is the all zero check for hpke. The second one was for the nonce reuse, the really severe vulnerability also in hpke. Again, these are used by Signal and others as well, OpenMLS and so on. One for a normalization API to make sure that signatures using ECDSA are non-malleable. And again, this is not really a bug, but more of a hardening thing. And it does break interoperability, so I made sure in my pull request to make sure that the API did not break interoperability, but it offered a separate API for non-malleable ECDSA signature verification and issuance. And then a fourth one to remove the premature double clamping in ED 25519. So each pull request contained a precise description of the vulnerability, a reference to the relevant RFCs, and a working fix with tests. Cryspen's reaction was to block my GitHub account from all of the repositories, close all 4 pull requests, and apply the same response to each before closing them. The responses were that the fixes to their critical vulnerabilities being deployed by Google, Signal, and OpenMLS with tests were policy violations that bypassed their documented security policy, constituted irresponsible disclosure because they put the community at risk, and they also said that they did not appear to be in good faith. And so I just want to remind everyone that the initial vulnerabilities submitted by Filippo Valsorda in 2025 and by Gu Jiang in December 2025 were submitted in exactly the same way as GitHub issues with pull and in Gu Jiang's vulnerability with pull requests, and they did not receive this treatment. Okay, but anyway, let's examine each claim. So the claim of a policy violation, hpke didn't even have a security policy. So I don't know where the policy is. There wasn't a policy in hpke. To be fair, libcrux had a security policy, and it was just one line that said email us. And so I don't know, like the other people that found the original vulnerabilities, they posted a GitHub issue or a pull request, and their submissions were immediately accepted. No drama occurred, and so I'm not sure why in this case they would react in this way, and also in half of the pull requests cite a security policy that didn't exist. The second regarding irresponsible disclosure. So they said, publicly disclosing security-sensitive code before a patch is ready puts the community at risk. So consider what was actually public. So these were bugs in open source repositories. So I'm not publishing a proof of concept. I'm not publishing an exploit. I'm publishing a fix for an open source repository. And so, you know, anyone who's been in security for even a little bit will know that if you have a cryptographic library that's being used by Signal and Google and OpenMLS, there are people that are much more capable than me, Nadim, in his home office that are trying to find these vulnerabilities. These people are usually employed by government agencies, and they are stockpiling these vulnerabilities in order to use them as munitions. And so those are the people that are putting the community at risk. And in fact, the existence of these vulnerabilities in open source software is what puts the community at risk, and not the good faith offering of pull requests, as has been the case with Cryspen's repositories in the past. That's not putting the community at risk. In fact, closing these bugs and leaving the code exposed to vulnerabilities and users as a result exposed to these vulnerabilities is what was putting the community at risk. The third claim that they made regarding was regarding good faith concerns. And so they said that based on the nature of the submission, it does not appear to be a good faith attempt to improve the project's security posture. But there was no difference between the way that these bugs were presented and the way that Filippo Valsorda's bug in November 2025 was presented. Description of the vulnerability, a citation of the relevant specification, a working code fix, and tests when tests were relevant. And so here, as I was saying, I don't know whether this was caught before my connection dropped, but this is a pretty transparent character attack, right? And so the point is to deflect. The point is to make it such that I'm the problem, because most likely this is like the presence of such numerous critical vulnerabilities is considered to be potentially damaging to Cryspen's reputation. And so an expedient sort of strategy here is to make it about the person filing the vulnerability, right? And so anyone who's been in the space for a few years, and I've been in the space for 15 years now, will know that this is not atypical behavior from vendors, especially vendors that feel that their reputation is under attack. But the thing is, we're doing them a service. Yeah, let's move on. So as I was saying, the initial reports were dealt with in the same way, but in our case, we received I received somewhat different treatment, despite the fact that I was merging fixes in the general public interest with tests when tests were relevant, right? And so because this was how the initial 4 vulnerabilities were actually handled, I actually was unable to submit additional vulnerabilities. So the vulnerability with ASGCM decryption actually causing a denial of service / NCCA violation was discovered after my account was blocked. And so even though I already had this is how I discovered that my account was blocked. Even though I already had worked on a fix for it and was just about to submit my pull request, I received a GitHub error stating that I couldn't submit my pro bono, bona fide, tested fix to their critical vulnerabilities, because I'm putting the community at risk and so on. Right. So by closing my fixes, Cryspen chose to leave 4 security vulnerabilities, more than 4 by that point, security vulnerabilities unpatched for weeks in some cases, or at least 1 week in all cases, in libraries that are depended on by Signal, OpenMLS, Google. And I just want to remind people that the nonce reuse vulnerability meant that any long-lived HPKE session using these libraries risked catastrophic nonce reuse, which includes full decryption and forgery in all messages with a security vulnerability. 1 week after these vulnerabilities were reported, Cryspen still hadn't issued a security advisory, had not requested a CVE, had made 0 communication to users, had not publicly acknowledged any of their vulnerabilities, and had blocked me on GitHub. You already know, like, my actions were pretty different. And so after closing these fixes that I presented, after rejecting them, Cryspen's CEO copy-pasted my fixes line by line in many cases, not all, into the code without any credit. So I think that speaks for itself. Eventually, more than a week after the vulnerabilities were reported and fixed, Cryspen did issue security advisories for some of them. And I want to talk about how their security advisories were handled. So the nonce reuse vulnerability, which leads to full decryption and forgery, was labeled as moderate, as a moderate vulnerability, even though on the CVSS 4.0, it would be a critical vulnerability with a objectively a 9.3 out of 10 score. And the description for the fix was fix potential overflow in context counter. That was it. So if you're using libcrux or you're using hpke and you're wondering why am I downloading the software update, you're downloading the software update because there's a fix for a potential overflow in a context counter. Does that tell you that your previous ciphertext was risking decryption? Does it tell you that you had a critical cryptographic vulnerability? No, it does not. And so their advisories had this one sentence for the entire vulnerability and documented it as moderate. No details section, no impact section, no mitigation section. The ASGCM crash vulnerability, denial of service / NCCA breaking vulnerability for 9 out of 18 cipher suites was described as fix panic. Again, it was labeled as a moderate vulnerability. absolutely nothing about any details, any impact, mitigation. All of their partners, all of their users were left with absolutely no actionable information, aside from the existence of an ambiguous, moderate level vulnerability that fixes an overflow in a context counter and fixes a panic. So, you know, we can go back to who's really being irresponsible and putting the community at risk, but I think it's pretty clear by this point. On February 12th, they issued, so we're getting to additional vulnerabilities. So stay tuned. It's not just a weird disclosure drama. So this is really interesting. On February 12th, they published a 1,570-word response titled "The Strength and Limits of Formal Verification." They implicitly acknowledged two vulnerabilities: the fallback v1 for LiPo's vulnerability, a fallback implementation for a platform-specific intrinsic. Translated, this means it produced wrong signatures on ARM CPUs. And v6, one in an unverified wrapper around Hackle star code. That doesn't even discuss what it is, right? What they did not mention is the one that caused signal. In fact, as I was saying, their official response didn't even mention the existence of hpke-rs or any of the critical vulnerabilities. They wrote 1,500 words about the strengths and limits of formal verification without mentioning 5 of the 7 vulnerabilities, including the most dangerous ones that led to plaintext recovery and so on, right? They only implicitly, obliquely mentioned 2 of them, and they were 2 of the less severe ones. Verified code, which was true as far as they knew. There were no bugs found in the verified code, as I've been very diligently stating in this presentation. The bugs so far have been in the verification, at the verification boundary, right at it or outside it. Although they would be, they wrote, although we would be very interested to know if any of our code generation tools inadvertently introduced a bug, and even more interested if the bug should have been caught by formal verification. Okay, so I'm very happy to announce that bugs were found in Cryspen's verified code immediately after this was published, because I was so interested in finding them after seeing how they were ignoring their bugs in the non-verified code. This gave me the motivation that I needed to press on with my research. And so let's talk about the bugs in the verified code. The first out of 4 was that their specification for MLChem decompression was actually completely wrong. So this is an interesting bug because it means that the formal mathematical model that they had for MLChem, the post-quantum key encapsulation scheme, was incorrect. And so even if you proved everything, even if every single proof was implemented and every single proof completed, you would actually be proving correctness against the wrong primitive, because fundamentally the mathematical foundation that you had defined for that primitive was incorrect. And in fact, not only that, but this vulnerability was in existence ever since 2024. It was merged by Cryspen's chief research scientist, full disclosure, my former thesis advisor, with the commit message spec. This was the first version of the spec file, so this bug has been present ever since the inception of this library. Bug number 2, the inverse number theoretic transform in the MLChem encryption specification was also completely missing. And so this is a really interesting one because the spec was wrong, but the Rust implementation that is meant to adhere to the spec was correct. And so the question that this brings up is, if the spec is wrong, but the implementation is correct, but the verification passed, then are they really comparing the implementation to the spec? I don't know. Because the whole point, the entire notion here is that you're supposed to be comparing the implementation to the spec. In this case, the implementation was miraculously correct, but the spec was wrong. And so I don't know if this was actually happening. And this is all within the components that are fully meant to be verified. This is not at the verification boundary. There's no asterisk. This is within the verification boundary, both of these bugs so far, as well as this one. So here, submitted this proof in a commit message that said remove admit. Admit is when you basically tell the prover to accept something as proven even though it's not. And so they removed the proof, they removed the non-proof and added a proof for the wrong thing, right? So again, the MLChem specification was completely incorrect. And finally, last but not least, they modeled the multiplication of x and y as the multiplication of x and x. So in their mathematical specifications that were being used for MLDSA, multiplying two integers was formally modeled as the squaring of one integer. So I don't know what to say. Like, this is, it doesn't get more fundamental than this. At the most fundamental level, their implementation, sorry, their formal specifications were broken, right? They were modeling the wrong thing. And if you were to ever verify anything against them, you would be verifying a potentially correct, potentially incorrect primitive, but you would be verifying it against an undeniably incorrect formal specification, right? So those four, none of these four bugs have been fixed, right? And so they invited scrutiny. I think in a week later, if you just look at the formally verified core, you'll see that there's a wrong mathematical specification for MLChem decompression. There's a including one where the multiplication of two numbers was modeled as the squaring of one integer. And this means that the specification, that check would basically be checking against something that had nothing to do with that. It had over 40 false axioms that were over 40 checks that were implemented as axioms. So the point here is that they marketed formal verification as providing the highest level of assurance, but if you look closely at the formally verified core, they're built that they're trying to model, and the documentation says yes, when actually, if you look at the proof, it's about something else completely. Cryspen's response to these bugs in their verified code, which were reported and found after they published a challenge for people to find bugs in their verified code, was that these do not appear to be security vulnerabilities, which technically, if you're looking at it from the implementation side, is true. But the point isn't that these are security vulnerabilities. The point is that the entire formal verification foundation was wrong. The point is that you had cases where you had an implementation that itself was correct, but it was being verified against a spec that models multiplication wrong. And so was it ever really verified against that? Was there ever really any comprehensive formal verification? Right? And so, right, strictly speaking, I mean, because you're not putting the models in the wild. People aren't executing lean models, or in this case, like FSR models. They're executing implementations that are meant to adhere formally to the specification, right? But the specification here was so egregiously, completely out of sync, even in cases like, number theoretic transforms are as basic as multiplication, that it brings the entire enterprise into question, right? And again, none of this stuff has been fixed, right? And so how did I find all these bugs? I just want to, before we move on to the last section of this talk, I found them all using NeoVim and a terminal on one side of my monitor, and on the right side of my monitor, the FIPS 203 and FIPS 204 PDFs with the formal NIST specifications for MLChem and MLDSA, and going through the code line by line and going through the specification line by line. That's all it took. That's all it took to find critical vulnerabilities and fundamental incorrect mathematical modeling of vulnerabilities of specifications in a formally verified library. Okay, so why did I do this? Why am I so passionate about this? Why does this matter? It matters because I have a PhD in formal verification, right? So I actually studied with some of the folks that work at Cryspen today, and with some of their competitors as well, and some of their business partners. And what I think this research shows is that you really need to, what I'm hoping it is a wake-up call for the industry to be more, to put it diplomatically, more clear and honest about the limitations of that research and of that technology. Because there is an arrogance problem. when you're relying so much on formal verification that you time and time again miss things that are caught or catchable rather by unit tests, right? And so the formal verification here actually discouraged practices that would have caught these things. The presence of formal verification, it's like the Titanic. So this is actually not the real story of the Titanic, but in the movie, the captain says, rush straight into the iceberg, right? The movie version said, in the real world, they tried to maneuver around the iceberg, but it was too late because he was so confident in the Titanic. And so this is basically the same thing. We're so confident in formal verification, rush straight into implementation. Don't bother with comprehensive unit tests and all the standard best practices that have been the case in the industry for the past 20 years or more. So like, to his credit, whether you agree with him or not, like Filippo Valsorda has pushed unit tests and integration tests and in-depth tests and all that for the Go cryptography libraries, right? Other researchers I think Dan Bernstein have pushed SuperCop and other technologies, and people at Google have pushed Project Witchproof and other stuff like that to do more thorough fuzzing and static code analysis. And so none of that was or very little of it, as far as I'm aware, was implemented here. Why? Because we have formal verification, right? So we are higher than these petty concerns, right? Like that's the sort of attitude that is often present in the field. And I hope that this work illustrates that this is highly misguided, and that if you're specialized in a type of mathematics that can be considered like a sort of elite specialization, that doesn't give you an excuse to ignore security industry best practices, right? So we should also be more clear about our claims. And the reason why this matters so much is because when you're actually claiming formal verification, because of the implication that these words carry, implicitly, it's more trustworthy, right? It's more verified. There's more, you're putting more of your reputation at stake because you're supposed to be like this sort of exceptional expert or carry this sort of exceptional expertise. And so when you're actually carrying your stack with this sort of level of security assurance, users are going to trust it more, and that means that you have to be more transparent and more careful with the security best industry practices that you end up implementing. And because of the sort of reputation that comes with formal verification, in this case, partial verification with absolute claims may actually be worse than no verification, because at least with no verification, there's no there's no undue level of certainty, right? No verification, we treat it the same as the other cryptographic libraries. But as soon as we start claiming formal verification, it becomes something that we sort of expect more of, right? And that can be dangerous, right? So this is why I'm coining this notion of verification theater, which is basically the practice of deploying formal methods in a manner that one, establishes machine check proofs for a subset of a system's code. Two, communicates these proofs using language that implies comprehensive coverage. And we saw that, right? I'm not making this stuff up. Like if you read the marketing claims of Cryspen's documentation, for example, every implementation in libcrux is formally verified, right? It's not true. And they have a footnote somewhere that shows even how that's not true. But that's still how it's communicated, and that's how it's communicated in the technical materials. If you look at their marketing website, it's even worse. And God knows what these sorts of vendors are telling business partners in private. And three, fails to disclose the verification boundary on or unverified components, or does not disclose them as clearly as is necessary. So this doesn't mean that that formal verification is like worthless and dumb and we shouldn't bother with it, but it means that deployed in a certain way, it risks causing the same kind of security theater so that Bruce Schneier defined more than a decade ago. So when they first started rolling out the TSA in the United States after 9/11, Bruce Schneier called the TSA security searches and so on security theater. Because we all know that you can buy materials at the airport store that you can make a bomb out of probably or something, but those aren't checked at the security check, right? And so it's an illusion to make people feel safe. But in reality, is it really doing that? It's unclear, right? I'm sure it is to a certain extent, but to the extent that people believe, that many people believe, it's unclear. So why does this happen? Let's be more realistic and more balanced. The thing is that all of these people working on, a lot of these people working on formal verification are research startups. And research startups have a unique set of pressures that make it more, I guess, understandable why this sort of thing happens. First, you have the funding pressure. So if you go to a funder and you tell them, you know, we verified portions of our code against certain properties, they're not gonna, I mean, for unfair and illegitimate reasons, they're not gonna think you're a winner, right? And so you wanna go there and you wanna be the big shot that says, you know, we're formally verified every component, right? And so this is what gets you grants and contracts, and that's really unfair and unfortunate, and I don't think funders should act like that, but that's how it is a lot of the time. And I know for a fact that actually, I won't say who, but some formal verification startups, not Cryspen, faced pushback for being honest about their formal verification guarantees, which I was shocked to learn about, and is very unfortunate. Secondly, we have the issue of complexity. It's just that people don't really have the attention to learn what you formally verified or not, so you might lose them. And third is the notion of competitive positioning. You know, it could be the case that you're more honest about your work, but others aren't, and then they get ahead because people trust them more for all the wrong reasons, right? So none of these things justify misleading your users, but they still kind of explain the behavior a little bit, right? So I did compare libcrux to one other library. I chose it completely at random. There was no bias here, just one that I heard about. And you know, it doesn't have to be this way, because the way that, so this is AWS's libcrypto. It has a bunch of verified components. This is Amazon, which, to be fair, is a much larger company than Cryspen and has way more money. But they were more clear about the scope. They were more conservative about the way that they handled axioms. And so, you know, there are some best practices here that other formal verification teams can adopt. Let's look at some other precedents as well. So CompCert, which is the verified C compiler, explicitly identifies the parser, assembler, and linker as unverified. They have a lot of academic scrutiny that sometimes finds bugs and often doesn't. They're much more open, and they, you know, I guess don't block people on GitHub for reporting bugs. And there's also a verified microkernel called SEL4, and they maintain a dedicated what the proofs assume page meant to communicate this stuff more clearly to a more general audience. And so, you know, you can't say that honest communication is not an established practice here, because in many cases it is, as we saw with, you know, other verified libraries, or, you know, other verified components that are not cryptographic libraries, like compilers or microkernels. You know, it's a choice, right? And so finally, I'm just going to conclude by saying that formally verified software creates a heightened ethical obligation for transparent disclosure. I think that if you're claiming to be formally verified, you should actually expect people to be more transparent. You should actually expect people to default to full disclosure, because you are asking your users to place extraordinary trust in your libraries. And so when that trust is violated, these users deserve well, I mean, I don't even think it's extraordinary candor, but they deserve a transparent dealing of the issues, and not for things to be reported in private in what is called responsible disclosure. If you're gonna have extraordinary claims about the security of your code, you should expect to also have an extraordinary level of transparency, especially if you're not documenting things as clearly as you should be. So the recommendations here are to have more explicit verification boundary documentation. One really interesting thing that I think could work is having the verification status of code components as machine-readable metadata in packages. This is an idea that I have. So like when you install something via NPM or Go or Cargo, there's like a machine-readable JSON file that tells you what's verified and what's not. I think this could be a good idea. I think it would be nice to have a standard like that. I think, you know, honest marketing language would also help a lot. Having complementary engineering practices, so not, you know, almost completely foregoing fuzzing or binary analysis or even unit tests or integration tests would be really helpful. And also, rewarding transparent disclosure instead of antagonizing and attempting to assassinate the character. Okay. So libraries carry an implicit promise, and when the libraries produce incorrect outputs, cause decryption failures, accept malicious Diffie-Hellman public keys, permit nonce reuse with catastrophic consequences, generate malleable signatures, reduce key entropy, crash. And the way to fix that is by being more open to transparent disclosures and being more clear in how you communicate the limits of your research. That's my talk. Thank you very much, and sorry for the, I'm not even sure I'm still online. Sorry for the technical difficulties.